Hello students, in this lecture we'll be discussing problems related to Biot Savart's law and its application. So we have a question 1 here which states charge Q is uniformly distributed on a thin ring of radius r and the ring is rotating about its axis with a uniform frequency of f hertz. The magnitude of the magnetic intensity at the center of the ring is the question. So here there's a charge that is given, charge is spread on ring, and the charge is given as Q and the radius is given as R. And the ring is rotating at a constant frequency F. We know, let us give some direction of the rotation. Let us give it as clockwise or anti-clockwise. We know movement of charge will give rise to current. So this is exactly equivalent to a circular loop which is carrying current, isn't it? Because we know movement of charge in a particular direction will give rise to current. And what is the magnitude of magnetic field due to a circular loop at the center? Magnitude of the magnetic field due to circular loop is given by mu naught I by 2R. From the concept videos, we have learned that if there are n turns, it is going to be mu naught Ni by 2R. If it is one turn, then the magnitude of magnetic field at the center is mu naught I by 2R. We need to calculate the current. So since charge is given, we can write current as equal to charge divided by time. And here we will be calculating something called as the orbital current. What current, students? Orbital current. Orbital current is nothing but the equivalent current produced due to one rotation, due to one complete rotation. That is called the orbital current. Equivalent current due to one complete rotation. That is called as the orbital current. And since we are calculating the current for one complete rotation, time will become equal to time period because we are calculating for one full circle, isn't it? So time will be capital T and charge is Q. And reciprocal of time period, we know it is frequency. So this is going to be Q into F. So current is equal to how much, students? Q into F. That can be substituted here. So it is going to be mu naught into QF divided by 2R. That is the magnitude of magnetic field intensity at the center. So that matches with option number 2. Next question. Current I is flowing in a conductor shape as shown. So let me draw a conductor here separately. And here we can divide into different sections. As many number of sections you want, correct? Or as per the requirement of the problem, you can divide the given section. So I can try to divide into 3 parts. One is the 3/4 of a circle. This is one I'll call 3/4 of a circle. And then you have this, which end is fixed and the other end is going up till infinity. That means it is a semi-infinite wire because one end is fixed and the other end is going up till infinity. So this I'll call it as say 2, which is semi-infinite. And third, correct? Third is also what? Third is also a semi-infinite from here. From here it is there, isn't it? This is 3/4 of a circle. And this end is also fixed. And the other end is going up till infinity. So this is also a semi-infinite wire. Now we have to calculate magnetic field at the center. See, before calculating magnetic field due to any section, we can mark even the direction of current. Before calculating magnetic field due to any section, first you make sure, correct, you identify, is there any possibility of magnetic field becoming zero due to any section or not? That you have to identify first. Not maybe it's not applicable in all the questions, but you make sure that, correct, you are doing this task. That is, you find out magnetic field, correct, due to any section is going to be zero or not. Yes, due to section 2. See, this is section 2 and this point O, where is this point O lying? Where I have to calculate the magnetic field? It is lying on the axis of the wire 2. It's lying on the axis of the wire 2. Are you following something? So we know magnetic field, correct, due to any structure on its axis is going to be zero, isn't it? Magnetic field on the axis of the wire is going to be zero, as seen in the concept videos with the help of Biot Savart's law. Since O lies on the axis of wire 2, magnetic field, correct, due to section 2 at O will be 0. So magnetic field due to section 2 at point O. At point O is going to be equal to 0 because that point O is lying on the axis of the wire. That's it. Now calculate what is the magnetic field due to this third wire. Magnetic field due to the third part. So if you just see here, this end is going up till infinity. This end is fixed. And the other end is going up till infinity. Now I have to calculate magnetic field at one end. So this is nothing but semi-infinite wire and we are calculating the magnetic field at one end and the perpendicular distances are. So we know the formula for semi-infinite wire, mu naught I by 4 pi into R into 1. For infinite it is 2, for semi-infinite it is 1. And what is the direction, people? Direction, as you can see, in the complete section, the current is in which direction? The current is in anti-clockwise direction. From the bottom, if you just start, it is in anti-clockwise direction. So the magnetic field is going to be in which direction? The magnetic field is going to be in the inward direction. It is going to be in which direction, people? Inward. So B3 is also inward. Now you can check out the magnetic field due to section 1. Due to section 1, what is a magnetic field? It's an arc. And what is the magnetic field due to an arc? Mu naught I by 4 pi r. R is the radius and it is given as small r, multiplied by angle subtended at the center, theta. So how much is the angle subtended at the center, students? The angle subtended at the center is equal to, here see, it subtends pi by 2. This part subtends pi by 2 and this another part subtends pi by 2. So total it is going to subtend 3 pi by 2. This is the angle subtended at the center. And as you can check out using right hand clasp rule, so it is going to be inward. It is going to be inward. So here what we have to do, B1 is also inward and B3 is also inward. So two vectors in the same direction. This is also inward, 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 inward. Two vectors acting in the same direction, inward, inward will add up. Opposite direction, subtract. Some other angle, we have to use parallelogram law. Because both are in same direction, that's why we need to add up. So the net magnetic field is going to be B1 plus B3 or B3 plus B1. And while doing so, what I can take out common? First, I can take out mu naught I by 4 pi r common. Left out is 3 pi by 2 here. And then what is left out here? 1. So 3 pi by 2 plus 1 and the direction is inward. This is the net magnetic field. So that matches with option number 1. Next question. Two similar coils of radius r are lying concentrically with their planes at right angles to each other. So he's telling that the two coils are there. They are concentric, means center is same, but their planes are such that it is perpendicular to each other. Maybe one plane, it is placed like this on the desk. It is placed one coil and one more coil is placed in the vertical plane. Are you following? So two coils are placed perpendicular to each other. So one coil can be in the horizontal plane, correct? One more coil can be in the vertical plane. So let me just draw it here. So coil 1 here, you can give any direction of current. It doesn't matter here because he is not given. So if I give current, say I1 as equal to I, and one more coil, there is another coil, coil 2. So that is placed perpendicular to this coil 1. So one coil in the horizontal plane and one more coil in the vertical plane. So this is carrying a current, say I2 equal to, it's given that one is I and the other is 2I. Common center because they are concentric. So you need to calculate the magnetic field at the center. You need to calculate the net magnetic field at the center. So we again know the formula. Magnetic field due to a circular coil at the center is given by mu naught Ni by 2R. Here number of turns are not specified. So we can assume the number of turns to be 1. So magnetic field is given by mu naught I divided by 2 into radius for both the coils is R. 2R, but as I told you, without direction, the problem is incomplete. So here, how do we calculate the direction of magnetic field using right-hand clasp rule, isn't it? So if you have a coil, you give either anti-clockwise or clockwise, doesn't matter. So here the coil is there, isn't it? There's a coil here. And if you just see, the current is in which direction? The current is in anti-clockwise direction. So I'll curl my fingers in the direction of the current. In the direction of the current, the thumb is going to be in the upward direction. That is my B1. That is my B1. Similarly, B2 will be how much? B2 is going to be mu naught into I. Current it carries is 2I divided by mu naught I by 2R. The radius is same R. But what is the direction, students? Direction is, so the coil is not placed like this, isn't it? The coil is placed like this. So as I told you in the concept video, see from here and calculate the direction of magnetic field. So from here, the current is in anti-clockwise direction. So if I curl my fingers, the direction is to the right, isn't it? Or it can be clockwise, it will be to the left, anything, right, left. If for the first case, if the current is in clockwise direction, then the value of magnetic field would have been downward. You can decide in any direction, doesn't matter. You can give either clockwise or anti-clockwise. So in this case, it is going to be to the right. So this is my B2. Ultimately, what is going to happen is you can see that B1 and B2, they are going to be perpendicular. They are going to be perpendicular. Angle between the two vectors is 90 degree. How do you calculate the net magnetic field? Same direction, add, opposite direction, subtract, some other angle, use parallelogram law. The diagonal is going to represent the resultant B net. And we know B net is given by the formula, a root of B1 square according to parallelogram law plus B2 square plus 2B1 B2 cos theta. Angle between the two vectors is how much here? Angle between the two vectors is 90. So cos 90 is going to be 0. So this whole thing becomes 0. So B net therefore becomes equal to root of B1 square plus B2 square. Now before putting the entire value, first you check out is there anything common or not. So here mu naught I by 2r, mu naught I by 2r is common. First, you try to pull out the common terms outside. So mu naught I divided by 2r. Left out is what? In B1 term, there is nothing left out. So 1 square, plus in the second term, 2 is left out. So it will become 2 square. 2 square 4. 4 plus 1 is going to be equal to 5. So B net is going to be how much? B net is going to be mu naught I by 2r. 4 plus 1 is nothing but 5. So it is root 5 mu naught I divided by 2r. That matches with option number 1. Next question. A straight conductor carrying current I splits into two parts as shown in the diagram. The radius of the circular loop is R. The total magnetic field at the center P. See, this is a very tricky question. Here there is a loop. See, this part of the wire is there, isn't it? This part of the wire, 3/4 of a circle. This is carrying current in this direction. It is in clockwise direction. So due to an arc, what is the magnetic field? Inward, correct? Magnetic field direction is inward. And there's another part, if you see clearly, this is that part which is carrying current in which direction? That is carrying current not in clockwise direction. It is carrying current in the anti-clockwise sense. So I1 is clockwise. I2 is in which direction? I2 is in anti-clockwise direction. So you need to be very careful. And we know magnetic field due to an arc. So first you can write down the formula. B1 is in which direction, people? B1, you curl the fingers of your right hand. It is going to be inward. And what is the magnetic field due to an arc? This 3/4 of the circle. So how much angle is it going to subtend? 3 pi by 2, isn't it? Pi by 2, pi by 2, pi by 2, as seen from the previous problems also. So B1 is going to be mu naught I1 divided by mu naught I by 4 pi r, radius is r, multiplied by the angle that it is going to subtend at the center, isn't it? See, what I'm going to do is, I am going to take a general question. It doesn't matter where you are connecting the cell, isn't it? Here the current comes I, and here the current leaves I. It can be any point. Here it's given 90, and this will be 360 minus 90, which is 270. It doesn't depend on the angle, students. It doesn't depend on the angle. I'll just show you here. See, this is current I. In the top portion, the current goes as I1, and in the bottom portion, the current goes as I2. In the top portion, the current will be I1, and in the bottom portion, current will be I2. Let us say this part of the R is going to subtend some angle, say theta at the center. Here it's given 90 degree, no? So it doesn't depend on the angle. So mu naught I by 4 pi R. So let me call this angle as theta 1, isn't it? This angle as theta 1 and this angle as theta 2. So you just see what I'm doing. Mu naught I by 4 pi R. I'll try to make the problem simple into theta 1. And what is the direction? What is the direction? The direction is going to be in the inward direction, inward cross. Similarly, what will magnetic field B2 be? B2 will be equal to, again, it's an arc. So it is going to be mu naught I. I is I2 by 4 pi, same circle, so same radius R, multiplied by the angle it is subtending, theta 2. And what is the direction? If you use a right hand, correct, right hand class rule, current is in which direction? Current is in anti-clockwise direction. So magnetic field is going to be outward. So it is dot. So what will be the net magnetic field, students? The net magnetic field is going to be subtraction, because the two vectors are acting in opposite direction. One is going to be inward and one is going to be outward. So two vectors in opposite direction. So we need to do what? We need to subtract. So it is going to be B1 minus B2. But before calculating the actual values of B1 and B2, what I'm going to do is I'm going to divide. I'm going to divide B1 by B2. So just carefully see here. B1 by B2 will be I1 by I2 into theta 1 by theta 2. Let us divide. Consider B1 by B2. So that is going to be I1 by I2 into theta 1 by theta 2. Now, how are, see, the wires are like, the wires obviously will have some resistance. And how are the resistance connected? Basically parallel, isn't it? So this is point A and this is point B. The top portion, correct? This is A and say this is B. So this black colored thing will have some resistance. Let us call that resistance as say R1. And this red part of the wire is also going to have some resistance, and that is also connected between the same 2 points A and B. So that will have some resistance, let us say R2. So as you can see that these two resistors are connected in parallel. In parallel, what will happen, people? Voltage will be same, correct? Voltage will be same. So how much is current? We know current is equal to V by R. Voltage is same. So therefore, voltage is constant. This implies I1 by I2 is going to be R2 by R1. Are you all following something? because they are in parallel. It's a general question. I1 by I2 will be R2 by R1. Now, how much is the resistance of a wire? Can you think what is the resistance of a wire? Yes, we know. Resistance of a wire is nothing but rho L by A. It depends upon the length of the arc also, length of the wire, isn't it? More is the angle subtended, more will be the length, isn't it? So this red colored wire, correct, is this much, correct? How much angle it is going to subtend? Theta 2. More is the length of the wire, correct? More will be the angle subtended at the center, isn't it? Because I'll write one more equation. I don't want to write many equations to confuse you, but still length, arc length is equal to, we know it is radius multiplied by theta. We know this arc length is equal to radius multiplied by theta. So here, or you can just understand R is equal to rho L by A. The cross-sectional area and the resistivity is same for both the materials. R is simply proportional to L, and the arc length, isn't it? The length of the wire is proportional to the angle that it subtends at the center. More is the angle, more will be the length. Simple. So R is proportional to L is proportional to theta. Therefore, what will happen is, therefore, I1 by I2 will become equal to R2 by R1 because they are connected in parallel, voltage is same, and current ratio will be in the inverse of resistance. And resistance is proportional to length of the wire, and length is proportional to how much angle it is subtending at the center. So R2 by R1 is going to be equal to theta 2 by theta 1. Therefore, I1 by I2 is equal to theta 2 by theta 1. That you can substitute it over here. Therefore, I1 by I2 comes out to be equal to theta 2 by theta 1 into left out is theta 1 by theta 2. So you can see that theta 1, theta 2 will cancel, and B1 by B2 will be equal to 1. That means B1 is equal to B2. So since B1 is equal to B2, correct, B1 is equal to B2. If you substitute here, therefore, what is the net magnetic field coming out to be? Both are same, so we can write it as B minus B, and that will be equal to 0. This is the net magnetic field at the center. So it doesn't depend on the angle, whether it is 90, 60, or 30, magnetic field at the center is always going to be 0. So first option. Next question, a long wire carries a steady current. There's a wire which is carrying a steady current. Now this wire is bent into a circle of 1 turn. Now this wire is bent into a circle of 1 turn. Let us say that radius is R, number of turns is equal to 1. And the magnetic field at the center of the coil is B. What he's telling students, magnetic field at the center of the coil is B. We know what is the magnetic field at the center. Magnetic field is given by mu naught Ni by 2R, but since there is only 1 turn, it is going to be mu naught I divided by 2R. This is the magnetic field. Done. Now it is then again bent into a circular loop of n turns. The same wire, first you bend it into 1 turn. Now you're taking the same wire and you are bending it into n turns. So don't you think the radius is going to shrink because it is the same length? With the same length, you have to bend it into n turns. So obviously the radius is going to shrink. The radius is going to shrink here. How many turns are there? Capital N is equal to small n number of turns are there. So radius is going to shrink. So obviously the radius will become R dash. And now you have to calculate the magnetic field at the center of the coil. Now magnetic field, if I call it as B dash is equal to mu naught, because n turns are there, Ni divided by 2 into R. R will also change, so it will become R dash. And how much is R dash? How do you relate R dash and R? Now, since you're taking the same wire and bending it into a circle, and then you're bending it into n turns, we can tell that length is preserved. Length will be same because it is the same wire you took. So length will be same. So if I equate initial length and final length to be same, what is the initial length? Length of the circle is nothing but 2 pi r. What is the length of the circle, students? 2 pi r in the first case. In the second case, no doubt it is 2 pi r dash, but like that, n circles are there. For one circle, it is 2 pi r dash. Like that, n circles are there. So 2 pi r dash multiplied by n. So 2 pi will cancel. Therefore, r dash is going to be equal to r divided by n. R dash is going to be r by n. Just put it here. So B dash is equal to mu naught into Ni divided by 2 into R dash, which is R by N. So N will go up. So this becomes mu naught I by 2R. N into N is going to be N square. And mu naught I by 2R itself is what, students? Mu naught I by 2R itself is the magnetic field, original magnetic field B. So this will be B into N square, or B dash is equal to N square into B. Therefore, option number D. Here you need to make sure that you are preserving the length. That is the idea here. Length is conserved, and with that only 2 pi r equal to 2 pi r dash into n. With that, you will calculate the new radius. Next question we have here. The magnetic field due to a current carrying circular loop of radius 3 centimeter at a point on the axis at a distance of 4 centimeter from the center is 54 micro Tesla. What is the value at the center of the loop? So he's telling that you have a circular loop and radius is given as 3 centimeter, and you are calculating the magnetic field on the axis at a distance of 4 centimeter. Distance from the center to the point on the axis, we call it, we denote it by x. And x is given as how much, students? 4 centimeter. And we are telling that magnetic field on the axis is 54 microtesla. So magnetic field on the axis is 54 microtesla. I have to calculate the magnetic field at the center of the loop. So we have one standard ratio. We have seen the concept videos that the ratio B center by B axis is equal to 1 plus x square divided by r square, the whole power 3 by 2. This is the ratio, isn't it? Now this I will substitute. B center is unknown. B axis is how much, students? 54 microtesla, and 1 plus x. X is nothing but 4. 4 square will be 16, and r square 3 square 9, whole power 3 by 2. So LCM, if you take 9 plus 16 will be 25. 25 by 9, whole power 3 by 2. 25 can be written as 5 square, 9 can be written as 3 square. So 5 by 3 the whole square into 3 by 2. So 2 will cancel. 5 cube, 5 by 3 the whole cube. 5 5s are 25. 25 into 5 is 125. 3 3s are 9. 9 3s are 27. Therefore, B center is going to be equal to 125 by 27 into 54. 27 ones are 27 twos are 54, and 125 into 2 is going to be 250 microtesla. This is the magnetic field at the center of the loop. That is option number C. Next question. Here the question is very tricky. Most of them generally go wrong in this question. So just see this question carefully. The magnetic field at the origin, we need to calculate the magnetic field at the origin due to a current element ideal vector placed at a point with position vector r vector. See here, I'll tell you the Biot Savart's law. See here. Now, if this is a wire which is carrying current, we take a portion of the wire, which is carrying current, which we call it as the current element. And then if we are to calculate magnetic field at this point P, if we are to calculate the magnetic field at this point P, then the position vector of P with respect to the current element, that was R vector. So what we used to do, people, we used to consider current element as something like origin, isn't it? Something like origin. So from that origin to that point P where we have to calculate the magnetic field, a vector directed from the current element to P is nothing but R vector, isn't it? Is nothing but R vector. And in this case, the magnetic field is going to be mu naught by 4 pi I into dl cross R divided by R cube, isn't it? But here, if you see, the question is not like this. The magnetic field at the origin, we need to calculate the magnetic field at the origin. So here, let me draw a diagram. Magnetic field at the origin. That means instead of calculating the magnetic field at this point, you are calculating at the origin. Due to a current element placed at a point whose position with position vector r vector. So current element is placed at some point, isn't it? There's a current element over here. We can consider this as the current element, and the position vector of the current element is given as r vector, isn't it? The position vector, you know the meaning of position vector, a vector directed from origin to that point P. So the position vector of the current element, that is a vector directed from origin to P, is given as r vector. But we are required to calculate magnetic field at the origin. So here, if you just understand what is this R vector is from current element to P, where we are calculating the magnetic field. But here, if you check, current element is here, and the point where we have to calculate the magnetic field is here. So if I draw a vector from the current element to P, current element, this is nothing but the current element. And the point where I have to calculate the magnetic field is at the origin. So a vector directed from current element to P. How much will it be, people? If this is R vector, obviously this is going to be minus R vector, isn't it? So therefore this R vector will change. So you have to be very careful. This R vector will become equal to minus R vector here, because the position vector of current element is R vector. But we have to find a vector from current element to the point where we are calculating the magnetic field. So these two will be opposite. So it is going to be minus R vector. So therefore, this is going to be mu naught by 4 pi I into dl cross minus r. So how much is dl cross minus r? You know this relation. A cross b is equal to, not b cross a, it is equal to minus b cross a, isn't it? Or minus a cross b is equal to b cross a, anything. Minus of a cross b is equal to b cross a. So similarly here, since R is becoming minus R, so DL cross minus R. So what will this become, people? DL cross R minus R is nothing but minus of DL cross R, and that is equal to what? R cross DL. Did you understand? DL cross R is not R cross DL. Minus of DL cross R is nothing but R cross DL. So R cross DL divided by R cube. This is the magnetic field. R cross DL divided by R cube, and that is there only the fourth option. So you have to be very careful here. A cross B is equal to minus B cross A, or B cross A is negative of A cross B. So we have minus of DL cross R, which is nothing but equal to R cross DL. So fourth option. Next question, PQ and RS. There are two wires. They are separated. They are two long parallel wires separated by a certain distance. M is the midpoint. M is the midpoint between these. The net magnetic field at M. So the net magnetic field at M is given to be B. Now the current 2 ampere is switched off. Then the field at now M becomes. So in the first case, there were two wires, isn't it? There were two wires. This wire was carrying current of 2 ampere, and this wire was carrying a current of 1 ampere. And he's telling that the magnetic field at point M was how much? It was given as B. Now, if you switch off the 2 ampere wire, then what will be the magnetic field? Case 1. So when both are there, isn't it? When both are working. So in case 1, what will be the magnetic field at point 1? Magnetic field due to long wire, what is the formula, students? It is given by mu naught I by 4 pi R into 2. 2 1s are 2 2s are. So it is nothing but mu naught I by 2 pi R, and magnetic field intensity is a vector quantity. So please be very careful with the direction. So what is the magnetic field due to 2 ampere wire? What is the magnetic field due to 2 ampere? So use your right hand thumb rule, correct? If I assume the distance to be, say, R, what is this distance from the wire to M now? R by 2, isn't it? So what will be the magnetic field, people, due to 2 ampere wire? Use your right hand thumb rule. Point M is to the right. So here the fingers are going in and here the fingers are coming out. So due to 2 ampere wire and to the right, I have to calculate. In concept videos, we have extensively discussed about the direction. You can use right hand thumb rule or class rule. I'm using right hand thumb rule here. So at point M, due to 2 ampere wire, it is inward. So therefore magnetic field at point M is due to 2 ampere wire, it is inward. Due to 2, I'll call it as 1. So due to 2 ampere wire, so it is going to be mu naught I is nothing but 2 by 2 pi R becomes R by 2. And what is the direction, students? Inward. And due to 1 ampere wire, due to 1 ampere, because two wires are going to produce magnetic field at point M. 2 ampere wire and one more 1 ampere wire. Due to 2 ampere, it is inward, and I have written due to 1 ampere, point M is to the left. So if I use my right hand thumb rule, the point M is to the left. So therefore my fingers are pointing outward. Therefore this is going to be mu naught I is 1 divided by 2 pi R. R is nothing but R by 2. The distance from 1 ampere wire to M is nothing but again R by 2. So this is R by 2. So therefore, this is going to be in which direction? Outward. So 2, 2 and 2, 2 will cancel. Two vectors in opposite direction. So you need to subtract, isn't it? Opposite direction. So what will I do? I'm going to subtract. Therefore, what will be the net magnetic field at M? Therefore, the net magnetic field at M in case 1 is going to be B1 minus B2. So this is going to be, if I subtract the 2, mu naught 2 by pi R minus mu naught 1 by pi R. That is going to be 2 minus 1 is 1. So mu naught into 1 divided by pi R. This is the magnetic field in case 1. He is telling magnetic field is B. Correct. He is telling I will calculate by my method how much is the magnetic field. Two wires are going to produce. It's not that simply he's written B and you also write it B. You simplify by yourself. How much is the magnetic field? 2 ampere will produce 1 magnetic field inward. 1 ampere will produce 1 more magnetic field outward. So net magnetic field at point M is going to be the subtraction. You calculate, and that he's calling it as B. Now in case 2, what he is doing, people? In case 2, now he's telling, now the 2 ampere is switched off, isn't it? So who will produce magnetic field? Only 1 ampere wire. Only 1 ampere wire will produce magnetic field at this point M, and the distance is R by 2. So what will be the magnetic field? We'll call that field to be B dash. So B dash is going to be only 1 wire. So it is mu naught I, that is 1 divided by 2 pi into R. R is nothing but R by 2. So 2 will cancel. You will get mu naught I, that is 1 divided by pi R. As you can see that mu naught 1 by pi R is same as B. Therefore, this is also B equal to B. Therefore, we can tell that B dash becomes equal to B. B dash is equal to how much? B dash is equal to B, and that is nothing but fourth option.